So let's begin talking about forces in two dimensions. Oh, sneeze. Excuse me. That'll be fun to watch in the video. You already know one example of forces in two dimensions. When friction acts between two surfaces, you must take into account both the friction force that is parallel to the surface and the normal force perpendicular to it. So far, you've considered only motion along the surface, but that's what we've been talking about. Now you use your skill in adding vectors to analyze two situations in which the force on an object are at angles other than 90 degrees. Now you've done this already in grade 11, right? We're just sort of extending the concept to this idea of equilibrium. An object is in equilibrium when the net force on it is zero. And that was the key idea that we sort of came up with from yesterday, right? Now, does it have to be at rest to be in equilibrium?
No.
Why not, Mike? You're right, by the way.
Because
what could it be doing?
constant speed.
Constant speed, exactly, right? Net force could be zero. That is still considered equilibrium. It's not considered static, but it is considered equilibrium. When in equilibrium, an object is motionless or moves with constant velocity. There you go. There's the answer. According to Newton's laws, the object will not be accelerated because there is no net force on it. You've already added two force vectors to find that the net force is zero. Equilibrium also occurs when the resultant of three or more forces equals a net force of zero. Figure 1a shows three forces exerted on a point object. What is the sum of A, B, and C, or what is the net force on the object? Remember that vectors may be moved if you don't change their direction. You guys know that from a long time ago. So if I took A and B and C and put them all tip to tail, the end result would be zero. Okay? And we would say that this object is in equilibrium. So figure 1b shows the addition of three forces, A, B, and C. Note that the three vectors form a closed triangle, which means there is no net force. No net force, so the sum is zero and the object is in equilibrium. Suppose that two forces are exerted on an object and the sum is not zero. How could you find a third force that when added to the other two would add up to zero? Okay? In other words, if I only had A and B, there is a net force, isn't there? Right? Right? The net force would be, I just got to fix this A a little bit. The net force would be from there to there, right? That would be my F net, which is oddly enough exactly the same length as this one here. The only thing that's different is what? The direction. Exactly. This force here, this one here that I'm shaking around, vector C, is known as the equilibrant. The equilibrant. It's the force that puts something in equilibrium.
That's like the keystone of equilibrium.
It sort of is, Mike. Well spoken. That is a wonderful analogy. It is the rock that holds it all together, much like yourself, Mike. The rock of the Clipper defense. Riley's not making any comments. Okay, so to find the equilibrant, first find the sum of the two forces exerted on the object. This sum is the resultant force R, the single force that would produce the same effect as the two individual forces added together. The equilibrant is thus a force with a magnitude equal to the resultant, but in the opposite direction. If you haven't highlighted that already, you should do so. That one that I just was talking about, right there, right? The equilibrant is thus a force with a magnitude equal to the resultant, but in the opposite direction. So all you really do is add the vectors together, find the resultant, and change the direction. That's how you find the equilibrant. It is? This is cooler than the monkey controlling the robot in Japan? I don't know about that.
You said add vectors, find resultant, switch direction.
Exactly. Figure 2 illustrates this procedure for two vectors, but any number of vectors could be used. And so once again, right, there's A, there's B, right? So you add A and B by doing what? Placing them tip to tail. Your resultant is that one there, and then you simply take that and flip it in the opposite direction, and that, my friends, is known as the equilibrant.
So it's the same as before. You use Pythagoras and just...
Yeah, it's or components, right? Do you see how every concept really goes back to all that stuff we learned in grade 11, and all we're just doing is just sort of like adding another layer kind of thing? We're like creating an onion. Like lasagna. Another fine analogy by Michael. The analogy king. Yes. Okay. So here's an example. And I think you have the example right there, do you not? Yes, you do. So, a 168 Newton sign is supported in a motionless position, in other words, it's at rest, by two ropes that each make 22.5 degree angles with horizontal. What is the tension in the ropes? Okay, so I'm going to have to draw this for you, aren't I? Okay, so we've got 168 newtons down, right? And it's supported in a motionless position by two ropes that each make 22.5 degree angles with the horizontal. So in other words, this right here is 22.5, as is this one, 22.5. Okay? Now, there's two ropes, so I'm going to call this T1 and T2, tension 1, tension 2. Is anyone feeling the need for some ibuprofen or anything? Feeling a little tense? And I'm going to call this one TV, and this one T, well, I guess it's T1V and T2V. And what do those stand for, do you think? Verticals, exactly. So T1V plus T2V, T1V plus T2V must equal the weight force, which is 168 newtons. The vertical components of those wires or ropes or whatever they are have to balance that 168, right? Is T1 equal to T2?
Yeah.
Absolutely, right?
There's two.
If the angles were different, would they be different? Would the tension of the ropes be different if one was 22.5 and the other was, say, like 50?
Yes.
Absolutely, right? Okay, for now we'll just make them equal. So in other words, what we really could say is that T1V is equal to 168 divided by 2, right? I'm just going to divide by 4, or divide by 2, sorry. Right. Okay, so using Pythagoras, I'm going to say that I've got opposite. 84, yeah. 168 divided by 2. So opposite is sine, opposite over hypotenuse, so I'm going to say sine of 22.5 is equal to opposite. My opposite is my T1V, and my hypotenuse is my T1. But what is my T1V?
84.
84. So sine 22.5 is equal to 84 over T1. So your tension is going to be 84 over the sine of 22.5. Now, is that going to be a number bigger than 88? We're looking for the tension in the rope. Is that number going to be bigger than 84, or is it going to be less than 84? It's got to be bigger. It's the hypotenuse, right? Let's make sure we're in degrees, Mike.
Oh, right, yeah. I am in degrees. That says an M in the corner. What does it say?
That just means you've got some sort of memory going on there.
Reset. Oh.
I get 219.5.
I get 105. You're actually high. Oh, I signed 2.5. 22.5.
It's got to be more, right? 219.5. Okay, so now here's a little program that I've got called Interactive Physics, and you can see here, I've got the block's mass is 25 kilograms, right? And let's just direct, whoa.
Wait, did you get 219.5? No. Okay. Whoa.
Fancy, yeah. Well, because it's all loosey-goosey, right? Which is why the tension is
The last one? Why did
0.
you divide by 2?
Why do I divide by 2? Because I've got T1V and T2V each are balancing the 168. So T1V only has to balance 84. So I got 84 here and 84 here.
Oh.
Okay, so you can see here as the angle changes here, I've got a weight of 245.3 newtons because I've got 25 grams here. Tension in A is 238. Why is it way more than this one?
Because it's like,
Because the angles are different, right? Set the block's mass, click and drag the attachment points of rope A, rope B attached to the beams. Oh, I see, okay. So I was dragging it in the wrong spot. So I can do this. And then what happens to the tension? Now they're getting more equal, right?
box over now.
How much tension is going to be in this one here?
That's
Oh, yeah, no.
Shouldn't it be more if it get down, if you go down?
But compared to the two, yeah, that one has more tension. But the other one, no.
has more tension.
Yeah. it's that one.
See, as this one goes down, right, what happens to the vertical component of it? It's smaller and smaller, which means that the tension in the rope must get bigger. So as I go up, the tension gets smaller, right? If I move this one over, right, it's going to get to be a whole lot more because the vertical component is bigger, right? Alrighty. So there are 4 practice problems there. How about you guys try the first 2, and then I'll give you some answers. Try those first 2 as sort of practice ones. No pressure. Don't get all. No, I won't even say. Let's have a look. The sign from the preceding example, was it 168? Okay. So now we've got basically you're doing exactly the same thing here except with what? A different angle. That's all it is, right? T1, T2, T1V, T2V, right? So T1V has to equal 84. Now it's sine 42 is opposite 84 over T1. So T1 is 84 divided by sine of 42. 125.5, Mike?
5.5.
Excellent. Okay. One thing you might need to be careful of is sometimes the problem might give you this angle here. What would this angle be here if these are both 42? How would you figure that out, Garrett?
96.
How'd you get that?
180 minus 42 times 2.
Yeah, 180 minus two different 42s, right? So it would be 96. Right? So you'd have to be able to convert that. You'd have to go 180 minus 96, would give you 84, and then divide that by 2, right?
180 minus.
You add the 242 on top of it, right? It's 142, that's 242. The rest of this is what is.
Okay, here's the second sample one. An 8 Newton weight has one rope exerting a force of 6 newtons on it. What are the magnitude and direction of the resultant force on the weight? And what force, magnitude, directions need to put the weight into equilibrium? And what, again, is that called?
Equilibrium.
The equilibrant. Equilibrant. So we're going to find the resultant. Yeah, absolutely. 8, 6, I don't even need a calculator because it's a 3, 4, 5 thing. That one's 10. Okay, there's no north, south, or east or anything here. So what would you call that? I would say tan, opposite over adjacent. Tan theta equals opposite over adjacent, 6 over 8. And so theta is the inverse tan of 6 over 8. I get 37 degrees, right? And how would you describe that? You can't use north, south, east, and west or anything like that. Why have you got your headphones on there? So maybe you should. Yeah, maybe you should, yeah. Okay, so I'm going to call that 37 degrees right of vertical. Okay, 37 degrees right of vertical. But we want to know what the equilibrium is, so we're going to flip that, right? I guess technically it would be
37 left vertical.
Well, it would be like this, right? It would have to be 37 degrees left and up, vertical, right? They didn't really give you a very good opportunity to sort of describe whether it's up or down or whatever. So when you get things like that, it's a little bit challenging to sort of describe the direction. Probably left of vertical would be fine. Left and up of vertical. Right? Okay. 3 and 4 are a little more challenging. I'll give you a few minutes to try those. The question is how you do the flipping. And here's where it's so easy now that I've shown you components, right? So let's just go ahead and figure out the components. Did you guys label these like F1 and F2 or something like that? Okay, whatever. So 2 roots pull on a ring, one exerts a 62 Newton force at 30 degrees above the horizontal, so this one is 62, and the other is 62 Newtons at 60 degrees. What is the net force of the ring? So let's just call them F1 and F2. So I'm going to have F1x is going to be this guy here, right? So that's going to be the 60. So that's going to be 62 cos 60, right? 62 times the cos of 60 is 31. And I'm going to put my y over here. F1y is going to be 62 sine 60. $53.7. Okay, let's do the same thing for F2. F2 is going to be 62 cos 30. Which is, well, I know these. 53.7, they're just opposites of each other, right? This is y. This is 31 as well, right? Now, I've set it up so that they're all positive up and to the right. So the net force on the ring, you would have to actually do what? Add them together, right? You're going to have resultant x is going to be, that's the point, 31 plus 53.7, which is 84.7, and because it's the same numbers, 84.7, right? Now, if I actually had to do, it does say what's the net force in the ring, so I guess I actually have to do this. 84.7, 84.7, right? Only to match the picture here, right? Oh yeah, that's fine. So my r squared is going to be 84.7 squared plus another 84.7 squared. So my r is going to be
119.77.
okay. 119. We'll say 119.8. Okay, and clearly that's going to be 45 degrees, right? Hopefully you don't even need to do the math there. Well, because it's 84.7, 84.7, right? What are the magnitude and the direction of the force that would cause the ring to be in equilibrium? Now,
Wait, how do you almost work out again?
Because the x and y are the same. There's other ways to do it too, like your two angles is 30 and 60.
84.7 over 84.7 is going to give you 45 degrees. Okay? Now, if I really wanted to find, this is easy, right? So the equilibrant is obviously going to be down like that, right? All I have to do is take these r values and do what? Like what's the EX R value? The opposite of the RX value. If you're asked to find the equilibrant, and you are, right? It's simply the opposite of the result. But the easiest way to do that is take the opposite of the x and y components. So the opposite of 84.7 is minus 84.7. And the opposite, the equilibrant y, is minus 84.7 as well. You just take the opposite directions of the Rx and the Ry, right? And then just, well, you're going to get what? You're going to get E squared is 84.7 squared. I mean, in this case here, you're going to get what? Exactly the same thing, right? Well, you're always going to get the same number, aren't you? Right? Because the numbers aren't going to change, only the signs are going to change. Now, what if one is negative and one is positive? Well, then you've got negative and positive down here, right? You just change the signs on those X and Y's.
So how does that change the direction of the thing?
It would here, your direction would be 45 degrees below horizontal. Right? It'd be 45 below. Here it's the resultant is 45 above.
So
And it has to be
do you
equal.
even have to do it negative, or can you just take the opposite?
You could. In this case, it's so simple, right? But I just wanted to show you that all you do is you do that R on the Y. I think that's what you have to do now in example number 4. Yeah, here. So,
I didn't do this.
okay. You've got,
75.
you probably don't have time. You have time to finish it. You probably don't have time for me to do it. So what I'm going to do is I'll stop there. And that way at least the people that are showing up on Monday can see me doing this one. So
Shit.
I will stop there.